In this video, we're going to look at an example of finding an area of the surface that will be best expressed in polar coordinates when we try to calculate the integral. So let's say we want the part of the sphere, x squared plus y squared plus z squared equals 4, that lies above the plane z equals 1. So if we think about where this, what part of the sphere that we're interested in, what region it lies over in the xy plane, if I put in 1 for z, we get x squared plus y squared equals 3. So we can actually imagine a cylinder, x squared plus y squared equals 3, intersecting the sphere x squared plus y squared plus z squared equals 4, where that intersects would happen at z equals 1. So that part of the sphere lies over that region. X squared plus y squared is less than or equal to 3. That certainly is a region that we can describe more easily in polar coordinates. The radius of that circle is 3, so we know that our r values go from 0 to root 3. I said the radius was 3. The radius is root 3. So our r values go from 0 to root 3. The thetas go from 0 to 2 pi. We now need to express our sphere as a function of x, y. We solve for z. We only need the top half because we went above z equals 1. So we get the function as z equals root 4 minus x squared minus y squared. And then we can apply our surface area formula. So when we do that, our partials for x and y respectively look a lot alike. We'll just have an x in the numerator for the partial with respect to x and a y in the numerator when we do the partial with respect to y. If we square both of those and just combine those two together, we get x squared plus y squared over 4 minus x squared minus y squared, and then a plus 1 in front because I didn't do anything with that plus 1 that's in front. All right, so now here's our integrand. Notice we've got x squared plus y squareds all over the place. We know we can replace r squared with that when we convert to polar. So theta goes from 0 to 2 pi, r goes from root 3 0 to root 3. We get 1 plus r squared on top and 4 minus r squared on bottom. And then again, remember for polar, we replace the dA with r dr d theta. We can, again, split this into two separate integrals because our region has constants for both theta and r, and our integrand is expressible as function of r times function of theta. So we can split it into two integrals. It just makes this right integral really easy because that's just going to be 2 pi. This integral becomes, if we look at what's on the inside here, if I multiply top and bottom by 4 minus r squared, we just get 4 over 4 minus r squared. I can pull out a 4 out of the square root, it becomes a 2. So that's why we get 2r times 4 minus r squared to the negative 1/2. An antiderivative for that will be a negative 2 root 4 minus r squared from 0 to root 3. This will simplify to 2. And then this one simplifies to 2 pi, and we get 4 pi for our final answer.